Good morning, esteemed panel and everyone present here. So I am Aman Shakil Sheikh and I am here to present our paper on flight path planning in an environment with moving obstacles. So this paper actually is in continuation with our previous work in which we worked on guided RRT star algorithm, which tackled the static obstacles in the environment in path planning. So this time we are doing on the moving obstacles part. So this is a brief itinerary which we will go through. The introduction, the methodology which we are using, and the simulation which we have done and the results, followed by conclusion and the future scope which we are planning to improve on the algorithm further. So for flight path planning is basically before every flight we need path planning to ensure that the mission undertaken is in compliance with the requirements and it is safe and efficient path. So which is why we need the path planning exercise to be done before every flight takeoff and landing. So this is the methodology which we are using. So in the first step we generate a path in a static environment using guided RRT star algorithm, which was our previous paper. Once the UAV is following the path which we have planned before, so while following the path it continuously monitors its surrounding through various sensors which will look in the next slide. If there is any collision predicted, if there is some obstacle moving in the course of the flight and that is predicted, the avoidance algorithm is triggered and we divert our path, and once the obstacle is avoided we come back to the original path and resume our following the planned path. So these are various type of sensors which are used in environment monitoring, like ultrasonic sensors, LiDAR, IR, camera based visions, radar, and the newer technologies like AI based detection and time flight sensors. So this is how we actually predict the collision. So we have the initial positions of our UAV and we program the initial positions of the obstacle which we will be encountering, and based on that we calculate the relative positions and velocities of both the objects, and using those relative velocities and positions we calculate the time of collision using the formula given over here, and we added a small constant in the denominator so as to ensure that if both the objects are moving in same direction and along are collinear, so then the denominator will become 0. So avoid the failure of algorithm in such cases, we added a small constant 10 to the power -6 in the denominator. So once we have the time of collision, we go for the minimum distance which will be there along the path. So minimum distance from obstacle and UAV which will be achieved in the course of time. Based on the time of collision we predict if it is negative, then it is not possible for the collision, and if it comes out to be positive, then we will check for the further conditions to verify if it is encountering the obstacle or not. Once we have predicted the collision is going to happen, we go for the next step, which is collision avoidance. So in collision avoidance we take cross product of the relative velocities and relative position vectors and calculate a perpendicular vector. So the UAV will then move in the perpendicular direction of its planned path to avoid the encounter with an obstacle. And in case if there is a collinear vector, so cross product will come as 0. So in that case we generate a random vector and use that for the calculation of the avoidance velocity. And using that the safe distance and clearance distance, we plan a temporary goal for the obstacle, which it chases until while it is avoiding, and once it is cleared the safe distance from the obstacle, it will then again go back to the rerouting and resume its path which is planned before. So here we can see the simulation results which we have conducted for different scenarios of the collision. So first one is side-on collision, where the UAV is changing its course and going downwards and then again resuming its path over there. Similarly, for the head-on collision, it moves in a perpendicular direction, and in the chasing collision, where the obstacle is chasing the UAV from behind, it diverts its course to a random direction perpendicular to its path and then reroutes itself to the original path. So these are some other scenarios which we have tested for the same algorithm. We have also tested two obstacles at a time which are moving closely together. So it successfully avoids both the obstacles and then goes back to its desired path. So in conclusion, we were able to create an algorithm which successfully tackles the moving obstacles in the environment and reroutes its path to avoid those obstacles and then come back to the original path. So in future, we are planning to use this algorithm for more number of obstacles, as well as we plan to integrate the newer technologies like machine learning in predicting the course of obstacle, so we have better chance of predicting its motion and avoiding the obstacle further. So I would like to give credit to my co-authors Anshum Rankawat, Milan Kumar Pal sir and Rajiv Kumar Das sir for contributing to the paper. And thank you.
Any questions from the audience?
So for the collision, your avoidance.
Yes.
Actually, suppose the two targets oppositely they are coming, okay, in a particular point, and you have decided that this is the obstacle. Then what are the things how you decide that? What are the logic?
So when we run the simulation, we decide a course for starting and end point for the obstacle, and it is moving in along that path. So we know when it will encounter.
Now you are defined a path, or automatically adaptive based path selection procedure is there?
And so path is defined for both obstacle and UAV while simulation, and we just check if the algorithm is avoiding the obstacle successfully or not.
If multiple targets in different directions they are coming.
Yes, sir.
Here I have seen that there are only two targets in opposite direction.
Yes, sir.
But if I have a multiple your targets,
yes, sir,
and they are coming in a particular point, then how to avoid that?
So that will increase, like the function which we are using to avoid the algorithm, we will have to modify it for more and more obstacles, and that way we'll be able to tackle. So that will increase the complexity of the code. So which is what we are working on in upcoming time. So which is mentioned in the future scope as well.
There should be, because only two targets obstacle it is not worked through. So
yes,
multiple targets you have to find out.
Yes, sir.
Okay.
Any further questions? Okay, I have one or two questions.
Yes.
You have considered only the parameter.
Yes,
And the acceleration there, suppose the target is suddenly accelerating or something, whatever the obstruction is coming. I have seen only the linear relation
Yes, sir.
between the position using the velocity and time. It is
Yes.
straightforward.
Yes.
So if any of the, suppose your UAV or the obstacle that is accelerating, then what will happen?
So that is yet to be accounted in the code. So this paper focuses on the obstacles moving at the constant velocity. So,
But ideally that will not happen.
so ideally that will not happen, but we are building it step by step in the algorithm. So in the next step we will include the different scenarios, and even the random motion of the obstacles will be included for this.
Okay. And another thing, there are many this kind of, like the autonomous car we are
Yes.
seeing, Tesla or anything. This obstacle avoidance mechanism is very well known and well researched. So what is the or new thing that you are doing here from the research perspective?
Sir, in vehicles it is, we are moving on a 2D plane. So those algorithms are basically A star algorithms or D star algorithms are used in 2D space planning, but that is becomes difficult in 3D space because it is computationally very heavy to calculate the cost for every point in the 3D space. So which is why we used RRT algorithms over here.
Okay.
So which randomly generates a point and tries to find the path, and while we increase the number of iterations and give it proper constraints, so it becomes more and more efficient.
Okay, thank you.
Yes. Thank you.
Thank you for your presentation.